Dear students, in this module we will try to understand and get ourselves familiar and get introduction to what is quantum chemistry. And we have Professor A.K. Bakshi with us, and I will be asking questions from you, sir, from students' perspective, because I personally feel that quantum chemistry is actually very the students are really afraid of this subject, maybe because of the maths problem or something else, and then there is so much confusion between classical mechanics, quantum mechanics. So, I will request you to introduce what is this quantum mechanics.
See, you have very rightly said that students are often very much scared of this topic, because I personally feel that if one is clear about the concepts behind quantum mechanics, then there will not be any difficulty. Whatsoever mathematics comes in this, that is basically to facilitate those concepts. Now, you asked me about quantum chemistry. The first thing which one has to keep it in mind is that quantum chemistry is the application of quantum mechanics to the problems of chemistry. So, the more fundamental question is, what is quantum mechanics? So, now what is quantum mechanics? In this regard, most important thing is that quantum mechanics is a theoretical science. Everything we do in quantum mechanics is theoretically. But now the next question comes, it is a theoretical science of what? It is a theoretical science of microscopic matter. Now one may ask the question, what is so special about microscopic matter that you need a separate science? It is so because microscopic matter, in that case, dual behavior is very significant. Microscopic objects like electrons, protons, etc., they have significant particle character as well as wave character. Therefore, we cannot ignore any one of these two characters. So, therefore, we need a science which simultaneously takes into account both particle as well as wave character, and that is what is quantum mechanics.
Something called classical mechanics also we have studied. So, how is this quantum mechanics different from classical mechanics, sir?
See, classical mechanics is basically based on Newton's laws of motion, and that has been the mechanics which people have been following for years and years, centuries like that. Newtonian mechanics is, we also call that, years. So, classical mechanics actually is basically dealing with macroscopic objects in contrast to quantum mechanics which deal with microscopic objects. Therefore, I think in a very simple language, I will say that classical mechanics gives you the laws of motion of macroscopic, and quantum mechanics gives you the laws of motion of microscopic objects. Because one thing is very clear, one should understand that the word mechanics is common in both of them, and the mechanics means science of motion. So, both are dealing with science of motion, one for macroscopic, other for microscopic.
But this quantum, the name having quanta, so what is the significance of quanta in quantum?
One will have to really go into history as to how this quantum mechanics originated, because it originated sometimes in the 20th century, beginning of 20th century, in around 1920s. Till the end of 19th century, people had the feeling that classical mechanics is all what we should need to learn and it can explain everything. But then in the 20th century, certain phenomena were discovered, experimental phenomena were discovered, which could not be explained on the basis of classical mechanics. These include, black body radiation, then we have got photoelectric effect, then Compton effect, atomic spectra, heat capacity of solids, etc. All these experimental phenomena which were discovered, these could not be explained on the basis of classical mechanics, and therefore a big question mark came whether classical mechanics has some limitations, or what is wrong with, why is quantum mechanics failing, why is classical mechanics failing in this case. And then certain new developments took place, and especially the role of Max Planck was very important, who introduced a very famous equation, E is equal to h nu. That means energy is transferred or etc. in the form of quantas.
Quantas, I think that's where this originated,
and that's how all these phenomena led to many features. And the most important thing which concluded from these experimental phenomena was that radiation, that means light, has not only wave character, it has also particle character. That means the dual behavior of radiation was established. That was a significant breakthrough.
Another thing which comes to my mind is how this Bohr's atomic structure, the Bohr's model that we are familiar, there were failures in that, and then how that led to the evolution of quantum.
Yes, I think you have asked a very important question, that if we look at the history of atomic structure, we had Dalton's model, then we had
Thomson's was there, Rutherford's Bohr models.
Bohr model came sometimes in 1912 or 13, like sometimes around that time.
But neutron was not discovered at that time.
Neutron was not discovered. Yes, it was because Bohr model was only for hydrogen atom.
Hydrogen atom.
He proposed it only for hydrogen atom, electron and nucleus, that's proton. So that's basically what it was. So when these developments were taking place of atomic structure, simultaneously quantum mechanics was also slowly originating. Because as I said earlier, if you remember, I said that dual behavior of radiation was established. So from this, there was a very famous scientist which all must have heard, de Broglie. De Broglie said that nature manifests itself in two forms, matter and radiation. He said that if radiation has a dual behavior, then on symmetry grounds, matter should also have a dual behavior, and therefore he proposed that particle and wave character, and there is a very famous equation which everybody knows, lambda is equal to h upon p, which is called de Broglie equation. This equation is very simple. Lambda can only be of a wave, h is the Planck's constant, and p is momentum which can be only of a particle. So this embodies particle and wave character. So this came in 1923, because you asked, why I am telling all this thing is because you were asking about atomic structure. So when Bohr model had come in 1912 or 13, people accepted it, but it had many limitations. Why further developments did not take place except for Sommerfeld model? It was because in the Bohr model, electron was treated as a particle, which now de Broglie said that it should have a dual behavior. Therefore, you need to consider both particle as well as wave character of electron. That was important. And secondly, in Bohr there was a concept of stationary orbits. That means the path around the electron. Now, path cannot be found out because once it was established that light has a dual behavior and radiation has a dual behavior, it gave rise to what is called Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, you cannot determine position and velocity simultaneously. Therefore, you cannot know the path. Therefore, the concept of stationary orbits which Bohr had proposed, that was not correct. That had to be ruled out. And that is why further developments in atomic structure did not take place along that model of Bohr. Therefore, that had to be discarded, and altogether a new model which is called the quantum mechanical model of atomic structure was proposed. The essence of this model is that this takes into account both particle as well as wave character of microscopic objects.
So here also, if electron jumps from one to higher position, it will require energy, and if it drops, is it correct, or it will be?
It is the same, now, because Planck had already said that energy is transferred in the form of quantas. Therefore, if it jumps, it will absorb a quantum of radiation, or if it comes from higher level to lower level, it will emit radiation. This was also the principles of atomic spectrum.
But as such, the orbits are not there. It is like a diffuse boundary, and the concept of…
Yes, the concept of the orbits which were there in Bohr model, they are not true. Now the modern atomic structure, we talk about probability. Now we talk of the concept of orbital. Orbital is basically it's related to wave function, as students will study in the later modules. We talk about wave function, we talk about probability considerations. Therefore, the concepts are totally different.
All these S, P, D and F orbitals, so they are outcome of these equations that will be derived using the quantum.
Yes, quantum mechanics, because once quantum mechanics was established, then people started applying quantum mechanics to various problems. When they started applying to the problems of chemistry, we call it quantum chemistry.
So it can be applied to biology and physics?
Yes, there are books you must have seen. There are many books in the library about quantum physics. There they are applying quantum mechanics to physics. Applying quantum mechanics to physics means taking into account both particle and wave characters.
But again, to the microscopic systems there also. Similarly in the bio…
So all these are microscopic, unlike statistical mechanics. Okay, as I said that quantum mechanics originated from the failure of classical mechanics to explain certain experimental phenomena. The most prominent amongst these was black body radiation. Now there is a black body radiation. Black body is basically a hypothetical body which emits and absorbs all types of radiations. So for the black body radiation spectrum, as you can see here, it looks like this. Now this is the experimental curve, but classical mechanics could not reproduce or could not explain this curve, and that was a very big failure of classical mechanics. Similarly, there is a phenomena of photoelectric effect. When radiation falls on a metal piece, it emits electrons. Now this is a phenomena which is very well known, but it could not be explained very properly, and the explanation of the photoelectric effect was given by Einstein. There is a well-known equation, Einstein equation, which explains photoelectric effect, but that can be explained only if we assume that radiation consists of particles. So this is a very big thing. Similarly, in the case of Compton effect, where there is a scattering phenomena, as you can see here, the change in the wavelength which occurs when scattering takes place. Here also you can see that this explained in the shift in the wavelength cannot be explained on the basis of the wave nature of the radiation. This can be explained only on the basis of the particle nature of the radiation. So these phenomena, along with atomic spectrum and others, led to the conclusion that in all of them, explanation can be achieved only if it is assumed that the radiation has a particle nature.
So the next question which comes to my mind is, you also talked about statistical mechanics. So now we have quantum mechanics, we have classical mechanics. This difference I have understood, and maybe my students also have understood here. But what is this statistical mechanic, and how this is related to quantum mechanics?
Yes, I think this is a very good question, because there is often a confusion in the minds of the students regarding the difference between quantum mechanics and statistical mechanics, and of course also classical mechanics. As I already said, that quantum mechanics is basically a theoretical science of microscopic objects. Why so? Because for microscopic objects, particle and wave characters are very important. You cannot ignore any one of them. But for macroscopic, bigger objects, classical mechanics is the answer. But as regards statistical mechanics, one has to keep it in mind that statistical mechanics basically deals with the bulk. If you have, say, 1 mole of atoms or 1 mole of electrons, how will you study it? You can't study it quantum mechanically. You can use quantum mechanical result as the input, but ultimately you have to take a statistical average, and that is what statistical mechanics does. So they are all dealing with mechanics, the science of motion. One is for macroscopic, one is for microscopic, and the other one is for a bulk matter. For example, in thermodynamics, the properties which we calculate, entropy or internal energy or enthalpy, all these are macroscopic properties. Statistical mechanics theoretically can calculate all these properties. Why enthalpy has so much value, why entropy has so much value. So that's basically the significance of statistical mechanics.
So using statistical mechanics, we will be able to calculate the bulk properties, am I right? And that's where the role of maths comes. That's where you have to use integration, differentiation, summation. So I think this
role of mathematics come in all these sciences. So that should not be very scary, because that is only to facilitate. You have to be very clear about the conceptual part. Now, for example, if you look at how quantum mechanics will operate, for suppose you have to study quantum mechanics for a particle in a box, hypothetical case, how will it work? You know, or if you have to study hydrogen atom, or if you have to study hydrogen molecule, there are basic rules which we will study in details later on, but there are 4 basic rules that whenever you have to study any system quantum mechanically, first step will be write down the fundamental equation, which will be Schrodinger equation. We will discuss it later on. So once it is written explicitly, second step is what are the boundary conditions for the system. That means what are the restrictions on the system. That is the second step. We have to define them. Third step is we solve Schrodinger equation in the light of the boundary conditions. And once we solving means there are 2 unknown quantities, psi and E. So these are the 2 quantities which we get out of the solution of the Schrodinger equation.
and H is Hamiltonian.
H is the Hamiltonian, which is the total energy operator, and the solution of Schrodinger equation will give us psi and E. E is the total energy, whereas Hamiltonian H is the total energy operator. So once we get psi and E, then the last step is finding out the properties of the system. That we can find out from psi, because psi is called storehouse of information. Everything about the system, every information is contained in psi. Then using certain rules, we can calculate or we can extract that information. So that's basically how quantum mechanics operate.
If you talked about particle in a one box, suppose we take this example, if it is moving in x-axis or y-axis or z-axis, does this also the student has to keep in mind while solving?
This becomes important while writing the Schrodinger equation. If it is moving in x direction, the corresponding Schrodinger equation will be different. If the same particle of the same mass is moving in y or z direction, the equations will be different. Otherwise, basically the results would be same.
So all these things have to be just these 4 steps you have told is what will be
So I would personally feel that students should be advised to understand the concepts behind quantum mechanics rather than to be scared of the mathematics. And once you understand the concepts and the steps involved, I'm sure you can play with quantum mechanics. There is nothing to fear about.
I think you have really made this introduction to quantum chemistry, where not only quantum chemistry, but broadly it is more quantum mechanics. When it is applied to chemistry, it is quantum chemistry. When applied to biology, it becomes quantum biology. When applied to physics, it becomes quantum physics. And we also understood the difference between classical mechanics and quantum mechanics, and then how the statistical mechanics is different from quantum mechanics. So, in the subsequent modules, the study is going to be even more interesting. We will apply all this knowledge and learn about more things. Thank you, sir.